we stopped the lecture right here. So just started about talking about uh, the theory of general relativity. So the idea is you don't need to to know any of these Einstein equations or anything like that for this course, right? So all you just need to know is just get the concept behind it. What kind of thing that we mean from the general theory of relativity, right? So that's it. So that is enough. And then after that, I will briefly explain some of the phenomena that happens as a result of this general theory of relativity. So let me explain it in this way. Now in this diagram right here, you can see that there is an object right at the center, right here. And once you keep an object right at the center, so what has happened is, due to the mass of that particular object, the space around it is curved, right? Now this is the basic idea behind the general theory of relativity. So which means the mass will curve the space, right? So that's what happens according to the general theory of relativity. Now, so if you take an example about our solar system, now from the A-level physics, so we used to explain the motion of the planets around the solar system using the Newton's gravitational laws, and all of you know how to explain it, right? But according to the general theory of relativity, so what happens is you have a mass like this. So our sun is at the center of the solar system, and you know the mass of the sun is larger compared to all the other planets. And because of that, once you have the mass sun at the center of the solar system, the space around that get curved. So once you have this curved space, all the other objects like planets, asteroids, and everything will move around this curved space, right? So that's what happens according to the general theory of relativity. Now, to explain it, there is a small video clip which explains this very nicely. And this is actually so one of the presentations made by one of the famous physicists called Brian Greene to one of the TV shows actually. But there is a small part that explains the curvature of space and how these planets move around the sun according to general theory of relativity. So let me see whether I can take that. And for that, actually, the idea is how you can explain the motion of the planets using the general theory of relativity, right? So in that way, it is easy to understand what Einstein tried to explain, right, in more simple way. So I guess you can understand it in that way. And so if anybody needs, I will just share the full video. This is just a public video made by Professor Brian Greene from the Columbia University. So he was appearing in one of these famous TV shows. Maybe some of you know about that. Let me share the link with you. Anybody needs right. So let me share my presentation again now. Right. So this is another way of explaining the same thing, that this is for three-dimensional analogy of space-time. And you can see that there is an ant moving on a table, and there is a rubber sheet that we have put on the table. And if it is flat, you can see that the ant is kind of moving from here to here in a straight line without any issue, right? But what happens is, if you put some kind of weight on this rubber sheet, the sheet will get curved close to this mass, right? So I guess everyone can understand it. And when once the sheets get curved, then what has happened is when this ant try to follow the same path, because now the space is curved, he has to go through this path, or it has to go through this path, right? So that's what happens when you have a curved space according to the Einstein's theory of general relativity, right? Now the importance of this in astronomy and cosmology is that there are some strange things happens due to this theory. Now, if you consider a black hole that we have been talking, in the vicinity of a black hole, which means close to a black hole, there are several phenomena that can happen. And I mean, four of those four main features that I am going for, phenomena that I am going to talk here, is the number one is called time dilation. Due to this general theory of relativity and the curvature of the space-time and the gravitational redshift, and then there is something called event horizon, and the last one is tidal effects, right? So let's see about the time dilation. Now think about now this curvature of the space near the black hole has the effect of slowing the time itself, and that is called time dilation, which means if you go close to a black hole, your time gets slowed down, right? Now, to explain this, think about that you convinced one of your friend to travel towards a black hole, bringing a giant clock with them. Right? So you ask one of your friend to travel close to a black hole and ask to bring a clock with them, right? Now, what you would notice is that their clocks would actually be very slow down relative to your time. So you will see that their clocks are very slow, right? When they get close to the black hole, right? But however, your friend will not feel their time gets slowing down. So he will not feel it. But once you are looking at it, you will see that the time gets slowed down, right? Now, and there is something called event horizon for a black hole. So that is the limit that you have for a black hole. So once you get close to that particular limit, and if you pass through the event horizon, that is the distance from the center of the black hole to a particular point, which we call the event horizon. And if you pass through the event horizon, you can't come back from the black hole, right? So that's the idea. And so if your friend is get close to the black hole and approach towards the event horizon, you will see that when they get more and more closer to the event horizon, you will see that their time slow down more and more, right? And however, you would never see them cross the event horizon, right? So you will not be able to see that they are crossing the event horizon because the time gets slower, more and more, it gets more and more slower. And what will happen is, if you consider your friend, he would experience a rapid crossing through the event horizon and then plunge towards the black hole. So he will feel that he just crossed through the event horizon, but you will never see it, right? Because the time gets slowed down. And this idea is now actually experimentally proved that the time gets slowed down. And according to this general theory of relativity, if you consider a radio wave, there would be a delay of a radio wave that would be passing through a region where time ran more slowly. There is an experiment that we were able to confirm that the Einstein theory is correct within 0.1%, right? So it is this experiment right here that you have Earth right here, and here is the sun, and here is one of the space probes called Viking. And we send the radio signal from this Viking towards Earth, and Viking is on Mars, by the way. And when you send the radio signal, it has to go near the sun, and because the space-time is curved very strongly close to the sun because of the mass of the sun. As you see in this picture, this particular light ray has to go in this curved space-time, right? Now, as a result of that, you will get a delay, right? So this is one of the experiments that we have an evidence now that these concepts are correct, right? And then the second one is gravitational redshift. Now the first one is called gravitational time dilation, where the time gets slow due to the curvature of the space. Now the next one is called gravitational redshift. Now remember that we have talked a redshift before, that is called Doppler redshift, right? Now this one is called gravitational redshift. Now what this means is when you, so if I briefly tell the idea behind the gravitational redshift is that the light waves or any electromagnetic wave will be redshifted due to the curvature of the space, right? Now, so the light that is not moving directly away from the black hole will have its path curved towards the black hole. Now this is what happens. So the light will get curved, and because of that they will be redshifted, right? And if there is an object that is close enough to the black hole, none of its light will be able to escape from the black hole. So the light moving directly outward is infinitely redshifted. Right? So what happens is, if there is an object that is very close to the black hole, none of its light will be able to escape, right, from the black hole. Because of that, we used to tell that the light moving directly outward is infinitely redshifted. Now this two pictures kind of explains this idea. Now this picture A right here is a normal star, and there is a person right here sitting on a normal star and having a flashlight with him, and the light leaving the flashlight will equally spread like this, right? So this is what we normally expect. Now think about that. You have a flashlight and you switch on it. Normally the light rays will be spherically distributed for each direction, right? So that's what we normally expect. Now consider a star that collapses so that it is just a little larger than a black hole, right? So something like this, the picture B, an object which is a little bit larger than a black hole. Now what has happened is all the light except the one straight up curved back to the surface. Now you can see that all these light rays are curved back to the surface, close to black hole, right? So they will not be able to escape. And because of that, you will not be able to see these light rays from Earth. So they are curved back. So there is only one ray that goes straight up. Now, what will happen is when this star strings inside the event horizon, so if this goes inside to the event horizon of a black hole, then what will happen is the light beam that is directed to the upward, so that will also not go away like that. So nothing will come out from the event horizon, right? Now this is one of the reasons that we used to have this name called black hole, which means the light cannot escape from that. Now, so I use the word event horizon frequently. So let me explain what is event horizon. Now, if you think about this gravitational redshift, it is very strong close to a black hole. In fact, every black hole has a precise region within which light is unable to escape. And this is called the event horizon, right? Now, if you consider the radial distance of a black hole from its center, so there is a region which we called as Schwarzschild radius. And that Schwarzschild radius value is actually the value of the event horizon, distance to the event horizon from the center of the black hole. Now, if somebody passes through that event horizon, you will never be able to come back again, right? And that particular region where that we used to call that if you pass through it, that you cannot even come back, which means even the light is unable to escape, right? If the light is unable to escape, you can't even think about escaping, right? Any other thing cannot escape. The light cannot escape because light has the maximum speed now. So, and this region is called the event horizon, right? Now, this radius that you have for this particular region from the center of the black hole is called Schwarzschild radius. And actually, something that you have to remember is this doesn't refer to the actual size of the black hole, right? Since its matter has collapsed down into the center. So the actual black hole is even smaller than that. And the size of the Schwarzschild radius is directly proportional to the mass of the black hole, right? So which means if the mass of the black hole is higher, the Schwarzschild radius is higher. So which means for very massive black holes, you cannot go very close to them. So if you go very close and if you pass through the event horizon, then you cannot come back, right? Now, these are the phenomena actually that made these different fictions and stories, right? Especially about this gravitational time dilation and gravitational redshift are very popular. And for example, if you take a black hole which has a 3 solar mass in terms of its mass, this black hole has a Schwarzschild radius of about 9 kilometers, right? And there is a way that you can calculate it. And I expect from you actually to remember this equation at least. If not, you can get the same equation by simple Newtonian gravitational equations by applying this equality to find the escape velocity, right? So you will have V right here instead of C for the normal equation. So the Schwarzschild radius is normally given from this particular equation. So it is important that you remember this equation, which is sometimes can appear in your exams, right? So Rs is the Schwarzschild radius, which is given by 2gm over c squared. And this g is the gravitational constant which comes from the Newtonian gravity. And m is the mass of the black hole and c is the speed of light. Now you can see that 2g over c squared is kind of a constant, right? So this does not change. And if you take m is the mass of the black hole. So which means the higher the mass of the black hole, this Schwarzschild radius will increase. So which means higher the mass of the black hole, the larger the event horizon is. Right? So that's how it works. Now I have given you 2 examples here. And here is Karl Schwarzschild. He is the one of the German scientists who first demonstrate mathematically that the black hole is possible to determine the size. He said that we should be able to determine the size of the non-rotating black hole's event horizon. And actually, the actual proof of this one is different than what you have. You can do it from using normal Newtonian physics to get this equation, but actual proof is different than this one, which means you need some knowledge about the tensor calculations and those kind of things, but you don't need to know that. You can either remember this equation or just prove it from the usual equation where you used to have to prove the escape velocity of an object, right? The only difference here is for the velocity, you use the velocity of light. So that's it. And here are two questions for you. So I used to give some time for you to solve these questions, but for today, see, due to this time limitation, I'm going to give you the answers, but make sure that you do it yourself, right? And practice these kind of questions. So the question number 1 is, astronomers have traced the path of several stars near the center of our galaxy and found that they seem to be orbiting an unseen object dubbed Sagittarius A with a mass of about 4 million solar masses. And what is the size of its Schwarzschild radius? Now, what actually this question basically talks about the supermassive black hole that we have at the center of our own Milky Way, right? And that black hole is called Sagittarius A. And so astronomers were able to calculate the mass of that particular black hole, and the mass is 4 million solar masses. It's a huge black hole that we have at the center of the Milky Way. And what you need to know, find the Schwarzschild radius of that particular black hole. Now, by answering that question, you will get an answer. And the second question is, what would be the size of a black hole that contained only as much mass as a typical pickup truck, which is about 3,000 kilograms, right? And so something that you need to note here is something with so little mass could never actually form a black hole, but it is interesting to think about the result, right? Now, we will never be able to have a black hole out of a light mass like this, like 3,000 kilograms. But it is interesting to see what happens if you do the calculation. Now, all you need to do is 2g over c squared are constants. You just need to plug the mass, right? So here are the answers for the two questions, and these questions are also answered in the book that I have as the reference. So I took it directly from there. Now, the Schwarzschild radius for that supermassive black hole at the center of our galaxy is, if you do the calculation by plugging all the values, we can come as 1.18 times 10 to the power 10 meters. Right? You can see it's a huge distance, right, in terms of meters. Now, if you compare the sum of the distances that we have in the solar system, this is actually a distance about 1/5 of the radius of the Mercury's orbit around the sun, right? Now you can see that yet the object contains 4 million solar masses. Now this is why black holes are specific. So they are very small in terms of their size, but the density is huge, right? And even though the mass, they are so massive like that, this is the reason why we cannot see them without largest telescope, right? And if you take the other question where you have the mass of 3,000 kilograms, you can see the Schwarzschild radius is 1.33 times 10 to the power minus 23. And this is actually even smaller than the size of a proton, right? Now you can see it is not practical now. Nobody can get up to this point in a pickup truck, right? And it's not going to happen, right? So that's why this is not practical and not going to happen. And this is why when you have very massive objects with huge density, like black holes, this Schwarzschild radius and the event horizon is important, right? Because it's a large value. Right? So if you have the knowledge of astronomy and how to calculate it, you should not get this much close, right? I mean, if one day if you are going to go in a space shuttle and go towards the center of the Milky Way, you need to be careful that you are not going to go beyond this distance from the center of our own Milky Way, right? Because if you cross this point, so if I draw this, something like that. Let's say you have this Sagittarius A right here. Right here is the boundary that you have. This is the Schwarzschild radius. And so if you come up to this point, then you have to think, right? So this is that length. So it's a huge length, 1.18 times 10 to the power 10 meters. So the Schwarzschild radius. And this is your event horizon, right? So you need to be careful that if you are going to travel towards the center of a Milky Way one day, you should not cross this line, right? If you cross this, you cannot come back again, according to this theory of the Einstein's theory of general relativity. So that's the idea, right? Now, when Einstein found this theory of general relativity, he was able to explain some of the phenomena that we could not explain before. Now, one of those phenomena is this Mercury's wobble. So, which means even though we used to tell that all these planets are moving in elliptical orbits, so this planet Mercury, which is the closest one to the Sun, has a small wobble in its path, right? Which means it will, go a path like this in one time, and the next time the path will change like a small amount like that. So this will happens like this, and the path will be, it will start to go like that. And astronomers were not able to explain why this happens until 1916, where Einstein discovered or found this general theory of relativity, right? So this is actually due to the fact that you have this huge mass of the Sun, and the Mercury is very close to the Sun, and because of that, this curvature of the space from the Sun causes this wobble, and Einstein was able to very accurately predict the amount of change in the orbit from his equations in general theory of relativity, right? So, and this is one of the evidences that the general theory of relativity is correct, right? Now, this is another phenomena that happens. Starlight passing near the Sun is deflected slightly by the warping of the space-time, and you probably have seen it even one of these previous images. So what has happened here is, here is the light from a star, and because that when it comes so close to the Sun, the light gets curved and change the path. So the path is deflected, right? So when you look at from the Earth, you would see that the apparent direction of a star, that the star looks that it appears right here, but actually star is right here. So this is one of the phenomena that could happen, and actually this deflection of starlight is one small example for a phenomena called gravitational lens, right? Now I'm not going to talk about that, but you will see some of the effects when we talk about galaxies and galaxy clusters, and this is the starting point to talk about this effect called gravitational lensing. And so you don't need to worry about that because I'm not going to explain about that. Right. After all, now you can see that this phenomena or the theory of general relativity is important when you explain some of these astronomical objects, right? However, the next question is whether this is actually important in our day-to-day life. So that's another question that you have to think and you need to answer. Actually, even though you don't know about this, your Google Maps app that you have in your phone, in your computer, that you use to find the paths, it is accurate because of the general theory of relativity. Otherwise, what would happen is, for example, if when you try to find a restaurant one day, the location of the restaurant will be off by like around 7 miles per each day, right? If you do not take into account the corrections that you should make due to the general theory of relativity and the special theory of relativity, right? Otherwise, sometimes students think that these are not important for your day-to-day life, but actually somebody else has done this calculation for you, so that's why you don't need to worry. But what actually happens is, when you consider a GPS satellites, they rely on 24 satellites that are orbit around the Earth, and at least 4 of them are visible from any spot on the Earth. So you have 4 of the satellites, and each of these satellites carries a precise atomic clock. So there is an atomic clock that they carry on, and the clocks on the satellites are orbiting around the speed of 4,000 kilometers per hour. So this is a high speed that they orbit around, and because of that, there is a correction that should come from the special theory of relativity, because when something moves faster, the time also gets slowed down due to the special theory of relativity. And that's one thing. And the other thing is, these orbits of these satellites are actually 20,000 kilometers above from the Earth, right? So which means gravity is about 4 times weaker than the Earth's surface. So the gravity is weaker in these where you have these satellites compared to the Earth, right? Which means according to the general relativity, if you do a calculation, these clocks should tick about 45 millionth of a second faster than they would on the Earth. And you can see that the difference is very, very small, right? 45 millionth of a second due to this weaker gravitational fields that you have close to these satellites compared to our Earth. However, if you consider the net effect of both general relativity and the special theory of relativity, that will have a difference of 38 microseconds. If you take the difference, right, 45 microseconds, and then you have, I guess, 7 microseconds coming from the special theory of relativity, and both these are working in the opposite directions in terms of the corrections. And because of that, if you take 45 minus 7, you should get a 38 microseconds difference in each day, right? Now, you would think that this is a very small difference that you don't need to worry about it, right? And that is actually true if you are doing something in your day-to-day life. But what happens is, as a result of this difference, and if you did not take this into account for your GPS, when you do these GPS calculations to find the locations, what will happen is there will be navigational errors, right? And actually, positions would be off by about 7 miles in only one single day, right? So which means each day you have to do this correction for these clocks. And if not, what could happen is, now for example, if you didn't do the corrections for 1 week, then you are, so that will be like around 50 miles. And instead of you are in the southern province, your location will be in somewhere else in another province, right? If it is a country like Sri Lanka, right? You can see why this theory of general relativity is important in that sense. Right, so you can see that what kind of things that would happen close to a black hole. We have basically discussed about stellar mass black holes, but there are actually other types of black holes. Stellar mass black holes emerge as a result of this usual stellar evolutionary process. However, there are other three types of black holes. The next type is called primordial black holes. And what we believe is these type of black holes may have formed during the early stage of the universe itself, when the universe started, right? But we have not detected any of those yet. And the other type is called supermassive black holes. And supermassive black holes, as I mentioned you previously, supermassive black holes are normally located at the centers of galaxies, right? And they may actually contain, these galaxies normally contain millions or billions of solar masses. Sorry, not the galaxies, these black holes will have billions of solar masses. So they are very huge in terms of their masses. And that's why they used to call them as supermassive black holes. And then intermediate mass black holes. So that is another time. So we believe that these type of black holes may have occurred from merging two stellar black holes. So you merge two black holes and create a new one, so which will have an intermediate mass, right? So these type of black holes are called intermediate mass black holes. Right, so there is something called tidal effects near black holes. So I'm not going to explain this too much for you. And the next question is, now we have learned about the theories and different phenomena that could happen close to a black hole and different types of black holes. And we learned that time gets slowed down near the black holes, and what happens if you cross the event horizon, all these kind of things. However, the question is, theory tells all these things, but do they actually exist? Are there, do we have detected any black holes, right? Now, the answer for this one, if I were to teach like before 2016 or 15, the answer is we have not directly detected any of these black holes. But now the answer is we have direct evidences that we have black holes, right? So we have detected from direct evidences there are black holes within last 4 or 5 years. Now, normally the black holes cannot be seen directly since the light is unable to escape from them. So that is the normal phenomena that happens from inside the black hole. You don't get any kind of light, right? Because light cannot escape. And however, there is something that happens, is that gas being pulled down into the black hole may tidally heated and emit X-ray radiation, right? If you remember the image that I showed you in the morning, I guess it's back, right? This image right here, you can see that when gas falls close to a black hole, they get heated up and they emit X-rays like this. Now, this emission of X-rays is an indication that there may be a black hole, right? So what you need to do is then you have to use an X-ray telescope to detect these X-rays from the black holes, which will give you an idea and indirect evidences that tells you that the black holes exist, right? And the other thing is black holes also exerts very large gravitational pulls on close stellar neighbors, which means if you have a black hole and there are stars close by, these stars will feel this huge gravitational pull, right? And because of that, the motions of the nearby stars may provide indirect evidence for the presence of a black hole, right? Now, these are the ways actually that we tried to detect black holes until very recently. And this example that I have Cygnus X1 is one of those examples to explain that we have some binary star systems which we have one visible star plus a companion star that we can see only under X-ray wavelength. So which means there may be a black hole, right? If you can see X-rays. And here is that example. And then the second way of detecting black holes is looking at the motion of the nearby stars, right? Now, if you look at this particular image, this is what happens close to us at the center of our black galaxy, that you have a black hole at the center, and all the stars, if you draw their paths around this center of the Milky Way, you can see that when they get close to the center, so they change their path very rapidly, right? So which gives you an idea that there may be a very massive object at the center, right? So that is one indirect way of observing black holes. But now we have a direct way of observing black holes, and this is through gravitational waves. Now, if you keep an eye on the news, especially in the foreign news, you probably have seen that the person who made this gravitational wave observatory and detected these gravitational waves received the Nobel Prize, right? Even in one of the past years, I can't remember the exact year. And so this also came as a result of the general theory of relativity, because according to the general theory of relativity, any rearrangement of matter from spheres to any other shape will create a disturbance in the space-time, right? So what will happen is, if there are motions or rearrangement of the matter, there will be a disturbance in the space-time, right? Now, this disturbance is what we called as a gravitational wave, right? And what relativity predicts is that these gravitational waves should spread to the outward directions with the speed of light, right? So if you have gravitational waves, they should spread out with the speed close to the speed of light, right? Now, the problem with the gravitational waves, that even though Einstein predicted these gravitational waves around 100 years ago, these waves are tremendously weaker, right? According to his theory, these waves are very weak than the electromagnetic waves. Now, remember, these gravitational waves are not in our electromagnetic spectrum where we used to study, right? Gravitational waves is completely a different thing. The problem is that, according to the Einstein's predictions, these weak gravitational waves are very weak, and because of that, they are very difficult to detect because of this weakness, right? Now, theoretical calculations suggest that some of the most likely events is that merging of two neutron stars in the binary system, which is, which could be a merging of two huge masses, which could give off some gravitational waves, and maybe merger of two black holes and swallowing of a neutron star by a black hole, like that. If you need to have some kind of detection of gravitational waves, the masses that involved in these mergers should be maybe two black holes, or maybe neutron star and a black hole, like that, right? So the masses should be very huge. And in the last 4 decades, the scientists have been developing an experiment to try to detect gravitational waves. So they tried an experiment to detect these gravitational waves, and so they had this instrument called laser interferometer gravitational wave observatory, or in short, this is named as LIGO, which is like a telescope to detect gravitational waves. And this is that particular instrument. So it's a very huge one. And these detecting arms are actually around like 4 kilometers long along each side. And the idea is, you send a laser beam towards this direction and that direction as well. So if you have a small disturbances, there will be a path difference, right? And that path difference can be detected, and then you can say that there is a gravitational wave. So that's the idea. I mean, and they were actually able to detect gravitational waves on 11th February 2016 for the first time through this detector called LIGO, and they announced that. So according to their calculations, those gravitational waves are produced by the merger of two black holes, and this is the first ever time in the history that we got evidence of the black holes as a direct evidence, and also merger of two black holes, right? Now, according to their calculations, the black holes had masses of 20 and 36 times solar masses, and this merger actually took place 1.3 billion years ago. Even though they reached us like 5 years ago, it has happened billions years ago, right? So life takes time to reach us. And if you think about the energy conversion through this process, 3 times the mass of the sun was converted to energy. So it's a huge energy. But the problem is nobody knows how to use these gravitational waves or store those kind of things, right? And here are the original waves that they detected. So they had actually 2 detectors. One is in Washington, DC, and the other one is called Hanford, the second one. And then they had the predicted type of wave, and their observations are nicely overlapped with the predicted curve, so that they can exactly tell that they have detected the gravitational wave. And to make it confirm, they have another detector which is hundreds of kilometers away from the first detector. The idea is, if you detect something for the first detector, after a certain period of time, you should be able to detect the same thing from the other detector as well. And that's how you can confirm something, right? So that's why you have 2 graphs right here, and then you shift it and overlap it to see how it works. And you can see that it's a nice agreement with theoretical studies, right? So that's how they detected gravitational waves. And here is the diagram of that gravitational wave. You can see that this is a very simple setup. Even if you learn in the physics, you send the light wave towards this direction and it gets reflected and come back again. And you send the same thing towards this direction, then you come back again, and you merge those to see whether there is an interference pattern, right? So that interference pattern is the one that is important when you detect gravitational waves, right? So these are some details about that detected objects related to the detected gravitational waves. And then if you talk about the black holes, there is something called Event Horizon Telescope, which is actually not a one telescope, a collection of telescopes who tried to make an image of a black hole for the first time in the history, and they were successful in doing that in 2019, around 2 years ago from now. And they were able to actually image a supermassive black hole in the galaxy M87. And to end this section right here, so I guess it's close to 5, so I just need to finish this part. Now this slide basically summarizes, I guess, all the 15 lectures that we did, up to all that, like 12 to 15 lectures that we did in within past few months. Now you have many different stages of the stars that they have to go through, but all the stars will end up in the following 3 end states at the end, right? If you have a star with the main sequence mass less than 8 solar masses, by the way, this should be solar mass. All these question marks should be solar masses, so for some reason it is So if it is less than 8 solar masses, those stars will become white dwarfs, right? These are not like exact numbers, by the way, these predictions. And the final mass of the white dwarf will be less than 1.4 solar mass. Remember that this was the Chandrasekhar limit, right? And then if you have stars which have main sequence masses between 8 and 25 solar masses, the final mass of those kind of stars will be between 1.4 and 3, right? Which means they will become neutron stars. And if you have a main sequence mass greater than 25 solar masses when the star is on the main sequence, those type of stars will become black holes, right? So you can see that in order to have a black hole, the initial mass of the star should be highest, or should be very a huge one, right? So that's the idea. So this will conclude actually our series about the stellar evolutionary process. Now on the next day, so I will be talking about stellar motion and exoplanets in the morning, which means the planets outside our solar system. Now we have a good idea about stars, and also we talked about planets. So let's look at how we can detect planets outside our solar system on the next day, right? And also different types of motions that we have for the stars. So that will be a short section about different types of stars that we have, and also binary star systems. So that those are the three things that we are going to talk on next day. Binary star systems, stellar motions, and exoplanets, right? So those will be the three topics that I will be discussing, and I will try to finish that in the morning, and if time permits, we will start talking about galaxies in the evening, right? So that will be the plan. Right, so anybody have any questions up to here? Right, okay, so there is a question asking, is time freezes after the event horizon of a black hole? Yes, so that's what happens. Actually, what happens is when you try to cross when you are looking from here, you would never see that somebody crosses the event horizon, because time gets completely slowed down. You get very, very close to the event horizon, but the person who is actually crossing, he will feel it across the event horizon. Now, this is actually one of the stories that I also get to. One of the stories that was based onto this famous film called, I guess, Interstellar, right? Yes, Interstellar. Yes, it should be Interstellar. It's a very, very scientific film actually that they have. They even have a published paper for that in one of the sections. So it's kind of, black holes are always kind of interesting objects to look at always. But in reality, actually, it's